Okay, this is the last video in the series for the alcohol oxidation reactions. This video is reactions 3 and 4, which are the hot basic potassium permanganate. So this is using KMnO4. As our reagent. This is a very deep purple colored reagent, so it's kind of fun when we use it in the lab because of the color. And when it does its oxidizing, when it gets reduced, it's reduced to manganese dioxide or manganese 2 oxide, which is kind of a black precipitate. It is kind of a sludge, and so it can be difficult to filter off, but it is trash safe. It's non-toxic. So that's the major advantage of this reaction, is that it is greener. Because the chromium reagent, the chromium 6, is toxic. The chromium 3 is not, but it's hard to get perfectly rid of all of the chromium 6, and so we have to dispose of that as hazardous waste. This is, however, a stronger oxidizing agent. Than any of our chromium 6 reagents. And so we do have to be a little bit more careful. So the con here, so this is the pro, is that it's greener and safer. I will say that, you still don't want to, touch potassium permanganate. It is a very strong oxidizing agent. But the con is that it is less selective than chromium 6. And when I say less selective, what I mean is that it's going to react with more functional groups. So in addition to oxidizing alcohols, so it will oxidize alcohols, but it will also oxidize alkenes and alkynes. And for those, depending upon the conditions, it can cleave them and turn them into ketones or carboxylic acids, or it can oxidize them to alcohols. So if it's colder conditions, it would be the alcohols, and if it's hot basic potassium permanganate, it would be a ketone or carboxylic acid. I don't expect you to know these or learn these in terms of what they would make. I don't expect you to be able to draw those products. But I do expect you to know that if you, for example, had an alcohol that also has an alkene present, that you would not want to choose potassium permanganate. And usually this is hot basic, so we often list it like this with the delta meaning heat, because what's going to happen is, especially if we use the hot conditions, it's going to cleave this and also oxidize this. So what we would end up with here, and again, I wouldn't expect you to draw this, but we would get the carboxylic acid. It would open that ring, 1, 2, 3, 4, 5. And so, yes, we would get the ketone here at this secondary alcohol, but we would also cleave this carbon-carbon double bond. Just as a side note, this reaction was used at one point for identifying alkenes, because you could cleave the alkene or the alkyne. Same thing happens with alkynes, except it would all go to carboxylic acid. And then you could take those bits that it divided into and identify those parts, and then you would know what the molecule is. It will also oxidize aromatic side chains. And this will basically turn anything with an aromatic side chain into specifically benzoic acid. And this includes all kinds of various functional groups that would be oxidized in this way. And it's really kind of fascinating because, you know, you could have this for example, and it's going to cleave it here and make the carboxylic acid. You could have alkenes, you can have lots of other things here, and it's just really going to obliterate that and turn it into benzoic acid and then oxidize the other side into whatever it might be. So here, fine to choose potassium permanganate as long as you don't have alkenes, alkynes, or aromatic kind of alkyl or alkenyl side chains present. Okay, so let's just, this is another one I'm not going to ask you to know the mechanism for. So let's just go over the basics where you would want to use it. So with our previous examples we've used before, our primary alcohol is again going to go to the carboxylic acid. You might have water listed, it might not be listed, but you would typically make a solution of, you know, some particular concentration of sodium hydroxide in water, and you would make sure the solution was basic before you add the permanganate, because again, that is that deep purple color. And typically you're going to heat this, and that would give you, again, the carboxylic acid, because we have water present, so that's going to form that aldehyde hydrate, just like we saw with the chromium, aqueous chromium 6 reagents. And then that's going to get oxidized to the carboxylic acid. If we have a secondary alcohol, same thing as before, that's going to become the ketone. Secondary alcohol. Here we get the carboxylic acid. And here we get the ketone. So really, you could kind of add, if you wanted to, you could kind of combine reactions 1 and 3 because they have the same outcome. It's a primary alcohol. I'm sorry, reactions 2 and 4. Because it's a primary alcohol going to a carboxylic acid. And just know that the caveat is that if you have any alkenes, alkynes, or aromatic side chains present, you wouldn't want to use potassium permanganate. And then same or similarly here, for secondary alcohol, you could actually use reactions 1, 3, or 5, and they would all give you the same outcome. And of course, for the primary alcohol, with reaction 5 with the PCC and methylene chloride, that's actually going to allow us to get the aldehyde. So that's kind of the distinction there with those reactions. And that is our alcohol oxidations.